So
Ajay.
Ini Ajayi.
You can't rise in life if God will not help what you do. God won't help what you do.
Yeah, 223-165. What's the deal?
Who be somebody use this place they preach now? Thought I want param.
Hello, good morning, class. Can you hear me?
Yeah, good morning, sir. We can hear you, sir.
Morning, sir.
Morning, sir.
Good morning, sir. Good morning, sir. Good morning, sir. Morning, sir.
Morning, sir.
Morning,
Morning, sir.
Morning, sir.
Weekend, sir.
Starting our class now.
That's enough now.
Morning. Who's hearing my voice?
Morning, sir.
Come and be my sugar daddy.
Okay. All right, I'll be sharing the screen with you in a moment. Okay. I hope you can hear me from the other hand. Briefly, let's just run through what we have done so far. Under acid, bases, and salts of CHE 126, we've been able to consider the definitions of acids, bases, and salts and their properties. We're also able to consider the strengths of acid and bases. And we also talked about the pH concept. And under there, we talked about the negative logarithm to base 10 of the concentration or maybe the activity of hydrogen ions. We also talked about the pH concept with respect to strong and weak acid solutions and base solution. We also looked at hydrolysis. We defined that and we related it to salts of strong and weak acids and bases. And the last concept we treated in the last class was the concept of buffer solution. And there we defined what buffer is, what is buffer action, the uses of buffer, and how we can prepare them. I hope you can all hear me from the other hand. Can you all hear me? All right. I can see your responses. So today, we'll go to the concluding part of the buffer solution, and we'll look briefly at indicators. And then we'll just have a very short quiz. And that will be the end of my whole aspect of the course. Okay? So in that previous class, we defined what buffer is, what buffer action is. We also looked at this formula, which is pH equals to pKa plus. I intentionally left this plus there. This anion represents the concentration of the salt, and this denominator, that is the concentration of the acid. Under there, we looked at an exercise in which you were asked to calculate the pH of a buffer solution, and you may also assume no volume change. You are also asked to calculate the change in pH if 1 cm cubed of 1 molar KOH is added to the buffer. Well, it can also be either KOH, NOH, depending on what you are adding to the solution. It may not just be a base. You may as well add an acid to the buffer solution. And what will be the effect of the small quantity of acid or maybe base you introduce into the buffer solution? So let us look at the remaining part of that last class. In that class, we were able to calculate the pH to be 5.25. And most of you followed it properly, that we were able to get that using the equation that I previously wrote for you, this equation 14. What if you introduce a base into the medium, into the buffer solution? How would that affect the buffer? We said that the change in pH will be 0.03. So how did we arrive at that? So let us look at it together very briefly. I wrote the question again so that you can follow it. 0.065 molar sodium ethanoate is added to 0.02 molar ethanic acid to prepare a buffer solution. Calculate. I'll just go to the second part, which is the change in pH if 1 cm cube of 1 molar KOH is added to the buffer. Okay, the first thing you would do to solve this is you determine the new concentration of the, okay, I'm coming. You determine the new concentration of the base you had, not NaOH, it's KOH precisely. You determine the new concentration of this KOH, determine the new concentration of CH3COH, and that of the sodium ethanoate salt that you have in the buffer solution. And how do you do this? For the base part, which is the KOH, what you could have done is, remember that sometimes ago, you were taught to dilution principle. You were introduced to dilution principle, and the principle says if you have C1, that is the initial concentration you're working with of the solution, and V1, which is the initial volume that you're dealing with, it will be equal to C2 V2. And this C2 is the final concentration you're working with, and this V2 is the final volume you're working with. So if you have a case like this, how will you be able to solve this problem? For the base you have added to the solution, this is what you would do. The initial concentration of that base is 1 molar. You've been told in the question that you have 1 molar KOH. This is KOH. 1 molar KOH. So that is your C1. Your C1 is 1 molar. Your V1 is 1 cm cubed. If you convert 1 cm cubed to dm cubed, you have 10 raised to the power minus 3 dm cubed, if that is what you want to do. And for the V2, that is the final volume. You were told that you are preparing that buffer in 1 dm cube. That is, you have this 0.065 and 0.025 in 1 mole in 1 dm cube solution. That is what we mean by mole per dm cube. Certain mole in 1 dm cube of solution. You may as well be told that you are working with 1 dm cube of solution. So whether you're told that you're working with 1 dm cube solution or maybe 1 liter solution, it is still the same thing. 1 dm cube is the same thing as 1 liter. So let me clean this again so that you can see it properly. So your V2 is, you initially add 1 liter, that's 1 dm cubed, and you introduced 10 raised to the power minus 3 dm cubed into that via this base you have added. So what will now be the new volume of this buffer solution? The new volume will be the 1 dm cube plus 10 raised to the power minus 3 dm cubed. If you add that together, or maybe you first decide to convert everything to cm cubed for easy calculation, you have 1000 cm cube for what you already have, plus 1 cm cube you have added, and now you have 1001 cm cubed. That will be the new volume you're working with. It looks somehow insignificant, but you can also take that increase in volume into consideration. However, in your question, if you are told that you should neglect volume change, it means don't consider this volume. Just use this concentration of the KOH or the base or the acid you're given directly. If you are told that you can neglect the change in volume. Okay, let's move on. So I want to believe that you understand how we got this 1001 cm cube now. If you do your mathematics very well, C1 V1 equals to C2 V2. We know our C1, we know our V1, we know our V2, but we don't know our C2. How will we do that? Our C2 will be our C1 multiplied by V1 divided by V2. C1, our C1 is what? C1 is 1 molar times what is our V1? You can decide to convert this V1 to dm cube. What will you have? That's 10 to the power minus 3. Divided by what is our V1? It is 1001 cm cube. And that is the same thing as 1.001 dm cubed. So you make that one your denominator, 1.001 dm cubed. If you press your calculator, you will get something like 0.000999 and so on molar. That will be the new concentration you are working with. And that will be the new concentration of the base you have introduced into that medium. Okay? Now, you know the new concentration of the base you have introduced into that medium. Remember we said that when you introduce a base into a buffer solution, the base can interact with part of the acid you have in that medium. And what will you have at the end of this? You have more of the sodium of the salt ion. That is the anion, CH3, COO minus. Possibly you have some water formed there. Okay? So if you have this, you have more of the salt, less of the acid, because that base you have introduced will react with some part of the acid in the buffer. So the volume or the quantity, or let me use the word, the number of moles of the acid you have in that medium will reduce. And the number of moles or the concentration of the salt you have in that medium will increase. And that is why we subtract the concentration will be other things that maybe 0.0, skip to this. For that of your salt, the initial concentration of that salt is 0.065 molar. If you, was supposed to add here. Was supposed to add here, not subtract. If you try to add to that concentration of the salt, you will observe an increase. That will be 0.06599 molar. If you divide, put what you have into this equation, that's pH equals to pKa plus log into concentration of salt over that of acid, you will have this 5.28. It may have some other decimal points behind it, but you will get an answer like this. Remember that in the previous slide, when we calculate the concentration, when we calculate the pH of that buffer, the pH was 5.25. Now, the new pH we have calculated is 5.28. 5.28. if you subtract the original pH of the buffer from the new pH of the buffer we have, you will get a pH change of 0.03. We'll get 0.03 as the new pH, as the change in the pH that you have observed. I hope you have followed what we have tried to do up to this point. Let me get some responses from you before we go to the last concept for today. Do you understand what we have done so far? Okay, I can see some responses. All right, okay. Okay, some of you said yes, some of you said no. All right, all right. Okay, let's take it this way again. Let's take it this way again. I've already said this is KOH. Okay, this is KOH. Depending on the base you are given, what I said before is just look at it very well. You were given the formula to use, and that is equation 14. That is pH equals to pKa plus log into concentration of the salt over that of the acid. This equation is very, very important. Just write the equation somewhere in your notes. The second step to take is calculate the original pH of that buffer solution. And that is what we have done. And how did we do that? We know we've been told that our Ka is 1.8 times 10 to the power minus 5. And from there, you can calculate your pKa, which is minus log to base 10 of Ka. So press your calculator and find out what your pKa will be. If you do it very well, you'll get something like 4.74 as your pKa. 4.74. So just take that pKa as 4.74. Don't forget that pKa. So let's introduce what we've been given and what we have calculated into this new expression to solve this question. pH equals to pKa, which is 4.74 plus log into concentration of what is the concentration of the salt? What is the concentration of the acid? The concentration of the salt is what we calculated by adding the number of moles of the base that we have in the new solution that we have created, the new buffer solution, after we have introduced the KOH into heat. That is what we have. That is 0.065 plus 0.000999. Just press a calculator, you will get the correct answer. So put that new concentration of the base here. That is 0.06599, or maybe you put another 9 there, divided by the concentration of the acid, which is this 0.019. I've shown you how we calculated it. You just subtract the new concentration we have for that of KOH you have introduced into the system. So you subtract it from that of the salt, you will have this 0.0. Subtract it from that of the acid, you will have that 0.019. So put 0.019 here. First, divide your numerator by your denominator. After that, take the logarithm of that. The answer you have, add it to 4.74, you will get 5.28. The original pH before you introduce this base into it was 5.25. Now you have a new pH, which is 5.28. 5.28 minus 5.25 what would that give you? That's 0.03. That was how we got 0.03 as the change in pH. Okay? I want to believe, just calm down and try to solve it yourself. You'll see that you'll be able to get the correct answer. Let's take a step further into the last part of today's class, and that will be the concept of acid-base indicators. So we'll be looking at indicators precisely. You might have heard the word indicator. Maybe when you were in secondary school, you did some titration, you had something in your burette, possibly an acid, and then maybe you were provided with a conical flask. You put your base there. Maybe you pipetted either 10 ml or 25 ml of your base into this conical flask. Then you added some drops of a particular substance. That reagent is called an indicator. So at the end of today's class, at the end of this unit, you should be able to describe what an indicator is and state appropriately how you'll be able to state appropriate indicator for specific acid-base reaction. If you have a strong acid against a strong base, which indicator can you use? If you have a strong base against a weak acid, and so on, which indicator will be appropriate for that type of acid-base reaction? So we'll be able to discuss that by the end of today's class, and you will have learned that. So just remember what you did in secondary school, or maybe what you did some times ago, or what you have read in some textbooks. If you didn't do that, maybe in WAEC or NECO, just remember what you have done before. So let's move into this concept precisely. So what is an indicator? An indicator is a substance that is used to determine the endpoint of an acid-base reaction. So we introduce an indicator basically to be able to observe the endpoint of our acid-base reaction. The indicator may be a form of dye, and it has some pH range. And that is why an indicator may not be applicable for all types of acid-base reaction, because they always have their own particular pH range. For phenolphthalein, its own pH range is between 8.3 and 10.5. Some texts may also expand it maybe from 8 to 10 or maybe to 11. And in a pH of 8.3 to 10.5, the color there, if you put it in that medium, it will be pink. But if the pH is not between this 8.3 and 10.5, you may have a colorless phenolphthalein. For methyl orange, the pH range where it can function properly is 3.2 to 4.5, and there the color will be red. But if the pH is more than that, then the color can change to yellow. You may observe some yellowish color in that medium. So an acid-base indicator can be a weak acid or can be a weak base, and it should also be partially ionized. Just look at this equation we have. This H, capital I and small letter N, this is used to represent an indicator, the acid form of an indicator. If it is ionized in water partially, because this is a reversible reaction, you will have this, you know what this is? This is hydroxonium ion, or maybe you call it hydronium ion, and the conjugate base, and that is the indicator ion in solution. Okay? The unionized indicator, this is what I mean by that. This HIN and this conjugate base, they have different color. The color of the indicator may be red, and when ionized, it may turn to yellow, depending on the indicator you're working with. So the color of the unionized indicator may be different from the color of the ionized form. That is the conjugate base. And Since this one is an equilibrium reaction, to find out the equilibrium constant, you can apply this equation, K equilibrium is equal to the concentration of the hydronium ion, that is more or less like saying the hydrogen ion in solution, and that of the conjugate base, the concentration, divided by that of the unionized indicator. That is how we can calculate the equilibrium constant for the indicator. And that is our equation 16. The acid base, there is a relationship between your pH and your pKa for the indicator. And the general relation is pH equals to pK subscript indicator plus 1, plus or minus 1. This plus or minus 1, it's as a result of we put this plus or minus 1 there to show that there's a particular pH range at which your indicator will function optimally. There's a particular range in which your indicator will be able to work effectively, and it should not be more than plus or minus 1 of the pKa of that your indicator. You understand when we look at, you understand it more when we look at table 2. You will see the pKa of some indicators in table 2, and we'll just look at it briefly. So we use this equation 15. Okay, maybe I didn't label the equations properly. So we use this equation to know the appropriate color where that indicator can be highly perceived, where you can be able to observe the color change properly. We have another concept that we call a universal indicator. A universal indicator, that one will contain 4 or 5 different indicators with different pH range. Maybe you have a methyl orange. Maybe you have a methyl orange. You know the pH range. We'll look at that in the table 2. You can have maybe bromocresol, may have phenolphthalein, and so on. Put them together, and you can have what we call a universal indicator. So it has a wide, it can sense a lot of solution. It has a wide pH range because it is a mixture of more than 1, 2, 3 indicators with wide pH range. All right, look at this table 2. And this table talks about the acid-base indicators and their pH range. I hope this is clear to you from the other end. We have Timor blue. They are essentially dyes. Methyl orange, bromophenol blue, and so on. We have phenolphthalein also. I'm coming, let me pick a pen. We have phenolphthalein, we have methyl orange. You're familiar with these two. We have methyl red, we have cresol, phenol red, and so on. Timophthalene. And you have their pH ranges. Now look at methyl orange. The pH range is between 3.2 and 4.5. Phenolphthalein is between 8.3 and maybe 10.0, 10.3, 10.5, and so on. It depends on where you are quoting those values from. And look at this phenol red. The pH range is between 6.8 and 8.4. So when you put maybe 2, 3, 4, 5 indicators together, you can actually form what we call a universal indicator. You can have a universal indicator. Okay. Initially, I mentioned that for each acid-base reaction, we may have appropriate indicator to use. So when you are having a titration of acid-base reaction, which indicator can function optimally in that type of acid-base reaction? So we'll just look at them very, very, very briefly. Okay? For a strong acid and a strong base, for instance, if you have a strong acid HCl and a strong base, let's say sodium hydroxide, for this type of reaction, you can use a methyl orange, you can use a phenolphthalein as indicator for this type of acid-base reaction. And that will be able to function properly. You'll be able to have what we call an accurate, a sharp end point. If you just put maybe 2 or 3 drops of the indicator there, you will have a very sharp end point. But what if you have what if you have a solution of a strong acid and a weak base? Which indicator will you be able to use for this type of acid-base titration or acid-base reaction? The one that can be applicable, the one that can work properly is you can use a methyl orange. You can use a methyl orange. And why will you use a methyl orange? Remember that when you have a solution of a strong acid and a weak base, the resulting solution that you will have may be acidic. So you will need an indicator that can sense an acidic solution that is not basically a strong solution, because it may not be a strong acidic solution again, due to the neutralization reaction that will have taken place between the strong acid and the weak base. So you will need an indicator that can work maybe between 4 to 6 pH range. And which indicator can work like this? Is it phenolphthalein? Just look at phenolphthalein. Can it do that type of work? No. Phenolphthalein cannot do that. But a methyl red can do a similar thing. A methyl orange can work in that kind of acid-base reaction. So if you have strong acid with a weak base, it's preferable you use maybe a methyl orange for that type of acid-base reaction as the indicator. Just put 2 or 3 drops of that indicator there. You will have a sharp endpoint. If you have a weak acid with a strong base, if you titrate a weak acid against strong base, you run what is in your burette. You run what is in your burette into your conical flask. If you do this very properly and you've put in your indicator there, then the resulting solution is not going to be neutral. You may likely have a basic medium, a basic solution. This is what you may likely have if you titrate a weak acid against a strong base. For instance, let's pick another pen. Okay, let's pick this. For instance, if you have, okay, give me an example of a weak acid. Did you mention something like this CH3COH? This is an acetic acid, this is an organic acid. Okay, or maybe you are using H3PO4. It's also a weak acid. If you react this with a strong base, maybe KOH, NaOH, and so on, what you will have as the resulting solution will be a slightly basic solution. So the pH will not be 7. The pH will not be equal to 7. You may have a pH that is greater than 7, maybe 8, maybe 9, maybe 10, maybe 11, and so on. And which indicator will be able to function properly in this type of environment? Which indicator will be appropriate for that type of acid-base reaction? Then you can start considering phenolphthalein. Phenolphthalein will likely work better in that type of acid-base reaction. A methyl orange will not work properly in that type of reaction. Okay? What if you now have a solution of a weak acid against a weak base? The endpoint may not be accurate. So you may not be able to have a suitable indicator for that type of reaction because you may not have a sharp endpoint. So you may read some textbooks, they may recommend maybe a phenol red or so. Well, it may work occasionally, but not all the time. So for this type of reaction, where we have a weak acid against a weak base, the endpoint may not be sharp, so no accurate endpoint, and there's no particular suitable indicator for this type of reaction. So most researchers try to avoid titrating and using indicator to monitor this type of acid-base reaction. Okay. All right. So far, we have come to the end of the class technically, but I have a quiz for you, and that quiz is already available on your LMS page. So just get to your LMS page, you will see the link to the quiz. It may not take you up to 30 minutes to solve the quiz, but you have to quickly run through the quiz. It shouldn't take you up to 10 minutes for you to finish the quiz. So go to the LMS page, click the link. It will still be available till 12 noon. So just try and access the link and solve the questions. You have 6 questions there, and the total mark for that question, the total mark is 8. This is just practice question. This is just practice question, and they are what we have discussed so far. So this is not your overall continuous assessment. I'm just trying to see how far you have been able to follow the class and how far you are able to undo some questions or some problems under this acid-base reaction. If you need to read textbooks, there are links to textbooks here. If you click these links, it will take you to textbooks you can download. You may not need to pay for them. You may be able to download these textbooks on your mobile devices, or maybe on your laptop, on your phone, or anything you're using to browse or to access this class. Let me wish you a very nice time. A new lecturer will be coming in by God's grace on Wednesday, and you'll be introduced to another part of this CHE 156. So, very briefly, maybe I can take one question before we call it a day. Okay, so if you have a question, all right, some of you are thinking that I should shift the timeline. Okay, just try. I will leave it on till, just try and access it if you can. But if you cannot access it, I will know how to extend the timeline. So there's no problem about the timeline. I can extend it for you, but as fast as possible, try to access it. It's not going to take you 5 minutes, 10 minutes. You just look at the question and pick the answer, except for 2 questions that are calculation. Just look at the question and pick the answer, okay? All right, if you have a question, let me see your hand. All right, just wait, patience. All right, Michael Jagede, I will allow you to unmute now. Michael Jagede, can you hear me? Michael Jagede, can you hear me?
Morning, sir.
Good morning. Is that Michael Jagede?
Yes, sir.
Or Michelle Jagede? I may not be able to pronounce the name very well. Okay. What is your question?
Sir, you know, some of the information in like the slides are incorrect. Won't it be confusing when we're reading?
Okay. I will upload the correct version so that you just run through it again. So go back to your LMS page in the next 20 minutes. You will see the new version there.
Oh. Okay, all right, sir.
Okay.
And also, sir, please, when is our CA likely to come up?
I may not be able to give you a particular time for your CA right now, but we'll deliberate on it and get back to you.
All right, sir. Thank you, sir.
All right. So you may lower your hand. Let me take one more question.
I was the first person you asked question.
All right. Timothy Adeyemi. Timothy Adeyemi, you can unmute. Timothy Adeyemi, you can unmute. Timothy Adeyemi, can you hear me? Timothy Adeyemi, are you there?
Yes, sir. Yes, sir.
Okay. Yeah. What is your question?
No, actually, I don't really have a question. I thought you had is just a kind of assistance. So that's why I just thought so.
All right, no problem then. All right. You may lower your hand. Okay.
Okay, sir.
All right. All right. So let me allow you to. Okay, let's see if you can take a poll. All right. Let me allow you to save your data, and you can go back to your LMS page and download the final version of our CH156 slide for acid, bases, and salts. So you can go back to the LMS page and download the final version in the next couple of 15-20 minutes. Let me wish you a very great day. Ensure that you are reading properly and you are practicing more questions. I may likely upload more questions for you on the LMS page. So always check your Moodle app or maybe the LMS page for questions, for quizzes, and try and solve them. It will also be advisable if you can have a group. If you can have a group in which you rub minds together, you solve questions together, you ask questions. I'm wishing you all the best in your CHE 156. Bye for now.